Now let's talk about basic identities and algebraic manipulation, Boolean algebraic manipulation. We'll discuss together. So there are basic rules for reducing Boolean expressions. Okay, so these are the tools, utility, properties, whatever way you want to think. These are the relations that you need to use to simplify Boolean expression. Now, at this point, let me explain why do we need to simplify a Boolean expression. By the simplification, it means that we are trying to reduce the size of the expression. In a turn, we are trying to reduce number of operations between related variables in the function. Why it is important? Because of the fact that in a digital design, all digital circuitry are electronic implementation of certain Boolean expression. Okay, so if a Boolean expression is large, means if it involves a lot of logical operation, that means you are having more electronics component there. As a result, you are increasing the cost of that specific component. On the other hand, if you can reduce a big expression into an equivalent smaller expression involving less number of functions, less number of logic operations between the related variables, it means you are using less electronic component in implementing that specific Boolean function. As a result, your digital component cost less. So this is a business aspect of putting importance on expression reduction. Okay, and to do that, to understand that process, we start with that mathematical foundation and properties and relations between different terms, and so that we can apply them onto a big expression, hoping to get it smaller. Okay, so let's start with an expressions or identities or rule. It says that let's look at this left hand column. Okay, x or 0 always reduce to x. Okay, and we can of course prove it by the truth table expansion, because this is involves like one variable and we know what the OR functionality or truth table looks like, and so on and so forth. So that's easy to prove. Now x or 1 is always 1. X or x, we can reduce that to x. X or x bar, it's always 1, for the reason that, let's say if x is 0, x bar is 1, so 0 or 1 is 1. If x is 1, x bar is 0, 1 or 0 is 1. So that proves itself, right? And then x bar is x, means if you take complement of an already complemented variable, you get back the original variable. Okay, so these are the one set of rule. And another set of rule, the right hand side column, we can see that x and 1 is always x, x and 0 is always 0. So we can prove it by truth table of the AND operation. X and x is always x. Again, x can be 0, 0 or 0 is 0. X can be 1, so 1 and 1 is 1. And x and x bar is always 0, because x can make either can take value 0 or 1, because this is a Boolean variable. So x bar will have 1 or 0. So either way, you are ANDing a 0 with 1, so that will result always with 0. Now, why I'm mentioning this left hand and right hand column? So one thing to notice here is, see this form, if you look at this equation relation, then you see that this left hand side of number 1 relation has a dual relationship with number 2 relation. See this x or 0, remember the dual definition of dual function. So x or 0, the dual of it is x and 1, right? And x dual is x. So this and this entire relation, we can see that the number 2 has its kind of a dual form of the number 1. So here is the observation. For if any relation is true, like left hand side equals right hand side, then its dual form also holds that relation. Means dual of this left hand side will be equals to dual of this right hand side. It's true for this relation 3 and 4, it's true for this relation 5 and 6, and 7 and 8. See, for each of them is a dual expression of each other, right? And it will be similar for these 4 relations as well, and we have certain name of them. Some of them are almost like your algebraic relation, commutative, associative, and distributive. But we have one very special for the digital Boolean digital logic world, Boolean algebraic world, which call a De Morgan's law. We'll come to that. But point here is these relations have been written such a way, like we can actually look at directly the dual of dual relation between 10 and 11. So let's say x or y equals y or x, right? So this is a commutative rule. You can change the variable position. It's the same expression basically. So you can just interchange the position of the variable, and similarly you can interchange the variable position for AND operation as well. Now again, see this left hand side of 10 is a dual form of left hand side of 11, and vice versa, right? And similarly right hand side is also holds the same thing. They are dual of each other, right? So so these are commutative rule, and this is very much similar to what the algebraic rule you have learned in your high school, right? Middle school or high school. So now associative rule is also similar to what we have learned in past in the algebra domain. So that holds also true in the Boolean algebra domain. So you can associate an OR, series of OR, in any way. So x or y or z is equivalent or same as x or y or z. So you can actually group them and operate them as you fit for. Okay, as you think it's fit to reduce. So they are your associative property. Okay, and similarly its dual become like x and y and z is same as x and y and z, right? So this holds. Now distributive also, it's similarly like you can distribute an AND over OR. So AND operation is here, and we are distributing over OR. So x and y or z is same as x and y or x and z. Okay, so it almost seems like a multiplication distribution over the addition in algebra, right? So this is kind of very easy to remember here, number 14. So all these 10, 11, 12, 13, 14, they're easy to remember. But 15 is somewhat little bit counterintuitive than what you have learned in algebraic, normal algebraic, general algebra domain. It's kind of, you can distribute a OR over AND. It almost looks like you can distribute a plus over dot or addition over multiplication, if you want to call it as addition and multiplication, but let's not call it because that's dangerous, because that's not a true thing, right? It is basically OR and AND. But visually, right, it looks like an addition and multiplication operation. So So that's why number 14 is easy to remember, because it follows that same multiplication operation distribution over addition. And similarly, we are doing an AND distribution over the OR operation. But here in the Boolean algebra, where we can distribute OR operation over AND, in the normal algebra, we never can do an add operation distributed over multiplication operation, right? So that's the difference. So number 15 is very tricky, so you need to be aware of this relation. And sometimes in a reduction process, like we kind of tend to overlook this relation and made our simplification steps much complex than what it should be, because at some point of time we forget that we can distribute odd over AND, because that's not naturally we have learned so far, right? This is very specific to the Boolean algebra. So please pay attention to number 15. So we can distribute OR over AND, and that becomes X OR Y and X OR Z. All right, this is distributive. Now the last but definitely not the least, that relation is called a De Morgan's relation. You need to pay very specific and special attention to this number 16 and 17, because this is possibly the most used relation in transforming Boolean expression. Okay, maybe it is a reduction, or it is just a transformation. Okay, so please pay attention to that and remember that. So it is saying that if we invert an OR relation between two variables, this is same as inverting individual variable and doing AND between them. So XOR, that relation we complement it, it is equals to we individually complement these variables x bar y bar and do a AND. Okay. Similarly, its dual is true, which is 17 relation. So we are doing an AND of two variable and complement that result. That is same as we complement the individual variable and OR them. So x and y whole bar is x bar or y bar. That's De Morgan. Now let's take an example, a very small example, right? So let's say I have a function. I haven't written this is what is the list of variable, but we should ideally write that. But let's assume this function involves three variable x, y, z, and its initial expression is x bar y z or x bar y z bar or x z. Okay, how can we reduce it to less number of operations? Okay, we want to reduce this expression. So what we can do, we can actually combine this x bar yz and x bar yz bar by identity rule 14. Okay, identity 14, and make it an xy bar. So we are kind of doing that reverse of the distribution of AND, right? Here we can say that it is kind of an x bar y with z and x bar y with z bar. So we are making them out xy bar and combine and grouping z or z bar plus xz, right? Now by identity 7, we can make it like z or z bar is always 1. So it becomes like x bar y and 1, which is basically x bar y. And we cannot do anything about xz, that remains in the expression. So your final reduction become x bar y or xz. Okay, so that's the reduction. Now again, let me explain in this also context. Let me elaborate that why we need that expression reduction. Let's say you have a function you need to determine, or sorry, you need to implement with an electronic component. Okay, and assume for time being each of this Boolean operation, like this inversion and 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 OR, has a corresponding electronic component to do that. just assume, okay? Don't need to be bothered about that, but how it is done, how it is in the electronic circuit, this is implemented. We'll review that later. But point is that each of these Boolean operation, let's see, they have a corresponding electronic component to it. So this means for this specific expression, you need to have 1 x bar, z bar, 2 inversion, and then 1, 2, 3, 4, 5, and 2 OR, right? So 2 inversion, 5 and 2 OR. That's what you need. So that means you are looking for 5 plus 2, 7, 9 electronic component, right? Versus if you compare the reduced expression, here I need 1 inversion, 2 and 1 OR. So we are looking for 1, 3, 4 electronic component here. So 9 component versus 4 component. So if someone is producing its electronic equivalent implementation of this function f using 9 component, of course cost is much higher because it's using more electronic component than someone is doing implementing the same function with less number of electronic component. Okay, so that will cost less, right? So that's the business aspect, and that's the more motivation for us to able to reduce function effectively, okay, as much as possible. Now there can be some more commonly used theorems of Boolean expression simplification, and again we kind of make it in left hand column and right hand column, and the relation is dual of each other, and these are not basic identities, but it is very easy to derive that relations from the basic identities, but they are widely used and they can be used directly. Okay, if you, let's say if you see some form of x or x y, you can straight reduce to x, and dual is true. X and x or y is basically your x. Okay, so and similarly xy and xy bar is practically your x. Its dual is true. X or y and x or y bar is x, and x or x bar y is practically can reduce to x or y, and similarly dual x and x bar y is your xy. So please try to prove them yourself with the basic identity. I'm not going to show it, but they are very easy to derive. Please do it yourself. Okay, derive these relation using the basic identities. But in a problem set, in exam, anywhere, you can use them directly. You don't need to prove it step by step. You can just directly use this reduction there. Okay. And there is one more interesting relations and I would say an expression reduction toolkit, which calls a consensus theorem. Okay, so this one says that if two different variable, here y and z, is ANDed with uncomplemented and complemented form of one another variable, like x in this case. So y is ANDed with uncomplemented form of the variable x, and z is ANDed with complemented form of that variable x, right? And there is OR, so xy or x bar z. If that you observe this kind of formations in expression, and also that same whole expression is ORed with yz, means these two variable, then we can go and just eliminate this yz from the expression. So in essential, if you see some formation like this, xy or x bar z or yz, then you can straight reduce it to xy or x bar z. Okay, so this is a consensus theorem, they call it. So if this holds true, its dual also holds true. So we can derive its dual form of each of this term, this expression, left hand side and right hand side, and that also holds true. Okay. Now we can prove it by again basic identities and other reduction steps that we have just learned in previous two slides. Let's try to do it. So we have need to come up with from this left hand side expression xy or x bar z or yz. Then what we can do, we can express this yz as yz and 1, and 1 I can do is as a x or x bar, right? So this guy, I'm introducing some term here. From left hand side, I'm actually adding this term before reduction. Just note that sometimes you need to do it. It is not that always true that you need to do each step into reduce. Sometimes in order to reduce effectively, you need to expand certain terms. Okay, expand certain terms. So that's very, very interesting observation in this theorem, and that is true, can be true for any other reduction problem. You can probably need to first go and expand first and in order to contract. Okay. So anyway, let's get back to this one. So we write down yz as yz and x or x bar, because with the basic identity we know this is reduced down to 1, and anything like yz ended with 1 is yz. So they are equivalent. Now we are expanding from here to writing down, we are distributing this yz and over this or, it becomes like xyz or x bar yz. With that, now we are grouping xy and xyz. Also, we are grouping x bar z with x bar yz. So we are grouping them. So we can do it, right, by the identity rule. Then we are so in normal algebraic term, it's called a taking out a common term, right? Taking out a common term. So xy is a common term here. We are taking it out. For the AND operation, it becomes within braces as 1 or z. Similarly, we are taking out x bar z here. It's within braces, it becomes 1 or y. So we know by basic identity 1 or something is always 1. So this term become xy and 1. This term become x bar z and 1. Effectively, that becomes my xy or x bar z. See, so that relation holds. So we can, if two different variable associated with another variable with its complemented and uncomplemented term, then if those two variables are associated together, like with through an AND in that expression, we can eliminate that term from the whole expression in order to reduce it. So that's consensus theorem. So that's all for this lecture 4. Please review your basic knowledge about coming from the Math 42. Try to relate that with this set of recap, I would say. And we'll talk in the next lecture. We'll talk more about like another ways of reducing more systematic way, I would say, of reducing Boolean expression.